What's up, everyone? How's everyone today? Good. Excellent. Doing good, doing good. Doing just fine. Alrighty. So, let's get started. So today we're going to talk about curvature. Of, well, curves, space curves, plane curves. That's 13.4. Okay. What sections does the exam cover? So the exam is, this is the reason I moved the homework up so much. So the exam is covering everything up until what we're covering tomorrow. Stuff tomorrow is not too complicated. But yeah, so the exam next week will be on Tuesday. And I'll send out an email with more info on this, probably tomorrow. Also, so I'm gonna have an evening review for the exam. Probably, I'm thinking on Monday. Might be in the evening, or I could do it earlier. So I was thinking probably I would hold the exam or the from 5 to 7 p.m. on Monday. I could also possibly do the review, say, so okay, normally office hours are until 1 o'clock. I could do the review from, I don't know, like 1 to 3 on Monday also. So I would just have a review session via Zoom for the exam, and I would mostly just be answering your questions about the practice problems and stuff. Yes, so that's the thing. So I probably more people would be able to attend the later one, but if I did the 1 to 3 one, I could record it, and people who aren't able to attend could, I'd have time to, upload it to YouTube, or you'd be able to watch it on the cloud before, with plenty of time to get any questions asked. Is there a way to get the answers for sample exam 1? Let me see if I might, those might be available. Let me see if I can find them. Yeah, I will probably have to email about that. Kind of annoying that they're not available, but yeah. So think about when you're available. I'll ask you guys tomorrow, and then we'll figure out when we're gonna have the review session. But yeah, it's gonna be sometime on Monday, probably either in the early evening, 5 to 7, or directly after office hours, probably. In fact, I would probably do them instead of office hours. So let's say probably until like 2 o'clock, I think, into class to 2-ish. But yeah, think about that, and we'll figure that out tomorrow. Okay, so curvature. All right, so the way I like to think of curvature is sort of the following. So imagine you have, suppose you're like looking down on some road and you're traveling along this road in your car. So here it's mostly straight, and then all of a sudden you get a really tight turn there. So if you're going along here, when you're traveling along here, along the straight part, the direction of the road is not changing much. So if you look at sort of the tangent vector here, it's mostly pointing in the same direction. And then when you get around here, the direction starts to change more rapidly. And the tangent vector is changing more quickly as you get there. So if you're in your car, you're going to feel that. When you're going around the curve, you're going to feel, some g-forces when you get to like the tight part of the curve, because you're changing direction rapidly and your momentum is throwing you against the side of the car, right? That's the g-forces you're feeling. And that's because it's turning sharply. The direction you're going in is changing rapidly. So that's often a very useful thing to measure in curves, is how quickly is the curve turning, how sharply is it turning. If you're moving along it, how quickly is your direction changing? So the way we're going to measure that is we're going to look at, so we measure the direction of the curve by looking at the unit tangent vector. So suppose your curve is parameterized. So the curve is given by, parameterized by vector function r of t. So we know r prime of t is a tangent vector, right? It's a vector which is going to be pointing in the direction you're going. But we don't care so much about the magnitude of it. All we care about is the direction it's pointing. So what we're going to do is we're going to turn that into a unit vector. And that's going to be the same length, 1, at every point. And we're going to look at how the direction is changing on that. So the curve is given by r of t. The unit tangent vector is basically just the tangent vector turned into a unit vector, right? The tangent vector is r prime of t. And then we're going to turn it into a unit vector by dividing by its magnitude. Magnitude r prime t. So we call this the unit tangent vector. So it's capital T. And it's a vector, so we put the arrow over it. So think of this as just the unit vector vector of constant length 1, pointing in the direction of travel. Right, it's tangent to the curve, and it's going to point in the direction you're going. Okay, so the way we can measure bendiness is to look at how quickly the unit tangent vector is changing, right? That is sort of a measure of the direction of our curve. So when the unit tangent vector is barely changing, the curvature is going to be low, right? The rate of change of the unit tangent is very slow. And when it's very bendy, the direction is changing very quickly. And so that's going to have, as we'll see, high curvature. So the rate of change of the unit tangent vector is a vector, right? So the rate of change of that is going to be a vector. What we want is just a number determining how bendy everything is. So we're going to take the magnitude of that. But not quite there for the definition, because this depends on the parameterization R of t. And remember, there are infinitely many ways to parameterize your curve, right? Some of them you could be going very, very quickly at a constant speed. Some you can be going very slowly. Some you could be going really fast along the straight parts and then really slow around the bendy parts or stuff like that. And so if we look at the rate of change of the unit tangent vector just for a given parameterization, that's going to change a lot depending on how you're actually moving along the curve, right? So think of it as driving along here. If you think about the G forces, sort of, you feel as measuring the bendiness, right? So if you're driving really slow around that curve, you're not going to feel many Gs, right? Because your direction is not changing very quickly because you're going super slowly around there. So what we want to do to standardize things is to use, like we saw yesterday, the arc length parameterization, right? So that we're going along this curve at a constant unit speed, and then look at the rate of change of the unit tangent vector in that parameterization. So that's going to be the best way to measure that, and that's in fact how we're going to define curvature. So if we parameterize our curve by arc length, also known as the unit speed parameterization, right? We're just moving along our curve at unit speed. So we define the curvature as the following. So it's kappa, that's a kappa. Not a very good looking one, but that's a kappa. So it's going to be a function of S. S is going to be a parameter because it's the arc length parameterization. So it's just going to be the magnitude of the derivative of the unit tangent vector with respect to arc length. So parameterized by arc length, find the unit tangent vector, take the derivative with respect to arc length, and take the magnitude. That's a curvature. The rate of change of the direction, right, with respect to arc length, the unit tangent vector. So for example, let me do this on another page, actually. So if you have a circle of radius capital R, it's going to have constant curvature. So at every point on the circle, it has the same curvature, 1 over capital R. And we're going to show that very, 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 very quickly. So we're going to parameterize our curve. So curvature doesn't matter where in space your curve is, right? A curve is bendy no matter where it's located, has the same amount of bendiness. So let's just put this guy at the origin. So we're going to do this in the plane. So we can parameterize this by x is capital R cos t and y is capital R sine t. Very quickly, Nicholas. Okay. Okay, so this is going to parameterize our circle. We'll be going around it counterclockwise, but it won't matter in this case. But this is not the arc length parameterization, right? If you take the magnitude of this, remember the magnitude of r prime of t, you'll see that we actually get r, and what we want is 1, right? So I'm not going to go through this process again. We did an example of this yesterday. But in fact, what we need to do to get the arc length parameterization, I'll call this R1 of S. Instead of T, we replace it with S over capital R. So you can check if you like that this has, you can take the derivative to get R prime and take the magnitude R prime. The speed is going to be a constant 1 in this case. Okay, so let's calculate the unit tangent vector, take the derivative, then take the magnitude, and then that'll be the curvature. So the unit tangent vector is going to be the derivative divided by the magnitude of the derivative of R1 of S. So the derivative is going to be R. So cos S over R is going to become negative cos 1 over R. We get the 1 over R from the S over R there. Sorry, a negative sign. And then R sine S over R is going to become cos S over R. And by definition, we already know the magnitude of R prime is 1 by design because it's a unit. It's a unit speed parameterization, arc length parameterization. Okay, so that's our t. Then we take the derivative of that. So t prime, or dtts, if you like. So we're going to get negative 1 over R cos S over R and then negative 1 over r sine SO over r. And so then the curvature is just the magnitude of that dt ds. And so you can just pull out the 1 over r, and you have cos and sine. Take the square root, square both of them, sine squared plus cos squared is 1. So you just get 1 over r. I went through that super quickly, but you can verify those steps. And I went through that really quickly because this is not how we're going to actually check curvature in practice for several reasons. But yeah. So the bigger the radius, the smaller the curvature, which makes sense, right? You have a really huge circle. If you're going around it at unit speed, your direction is not changing that much. If you have a really, really tiny circle, your direction is changing really, really rapidly as you go around it. And so your curvature is much larger. Yeah, you get the 1 over r from, so you have 1 over r times s inside cos. And when you do the chain rule, when you take the derivative, you multiply it by 1 over r every time you take a derivative. Correct. I would suggest going through it yourself. I kind of got to blaze ahead, but yes. No, so you take, so I should probably restate this. So it's in terms of s. So we're taking the derivative of t with respect to s. So t prime t is, so t of t is the unit tangent vector with respect to time, right? And so if you have your original parameterization, r of t, the unit tangent vector is the derivative divided by the magnitude. And it's going to be a function of t because your parameterization is in terms of t. But we want to first change it into arc length parameterization. And so it's going to be a function of s in that case. But well, in fact, I'm about to show another formula where you don't have to do the arc length parameterization. So let me do that. Okay, so actually finding the arc length parameterization is in most cases slightly impossible. So there are some very nice parameterizations where you can turn them into find an arc length parameterization, but usually you can't get an explicit formula for that. So doing all this is actually, it's actually not possible to calculate from this equation here. So it's convenient to be able to calculate curvature just from whatever parameterization you're given. And let's give an alternate definition of curvature that we can use no matter what parameterization we're given. So if we have the arc length parameterization, S is in fact a function of t. I wouldn't worry too much about this, but you can write S as a function of t if you're given R of t, right? It's the integral from 0 to t of the magnitude of r prime u given the original guy. So it's a function of t. And we know when you take the derivative of it with respect to t, that's the speed, magnitude r prime t. So by the chain rule, we have T prime T so we have an initial parameterization. We have some parameterization we're given, R of T. We can find the unit tangent vector in terms of that, and we can take the derivative. And by the chain rule, that's dt ds times ds dt. So dt ds and then ds dt we know is magnitude r prime t. Okay, so we don't quite have curvature yet because we know curvature is magnitude dt ds. But if we take the magnitude of both sides, so the magnitude t prime t is equal to magnitude dt ds times magnitude r prime t. That's a number already. Well, we can divide both sides by magnitude r prime t. And this dt ds we said is the curvature, right? Sort of forget about that. Now we have a function for curvature, which we can use for which we can use any parameterization we like. So if you're given some parameterization for a curve R of t, this is the formula for the curvature given that parameterization. So you find the unit tangent vector, you take the derivative, take the magnitude, divide by the magnitude r prime t. That's the formula for curvature. And that is a more useful one than the previous. But still, so this can be used in any instance. However, so it looks like a very simple formula, but in practice, sometimes finding the derivative of t is going to be really disgusting, depending on what your parameterization is, because you're going to have some nasty quotient rule, because then you're dividing r of t divided by magnitude r prime t, and then when you take those derivatives, you'll see when you do some. It can always be done, but it can be kind of nasty. So this is a good, useful formula, but there's a better one that I would remember that works better in almost every instance. It's almost always easier to calculate. So if you only have room in your brain for one formula, in fact, really no reason to remember the other one, I would remember this one. So the curvature is going to be r prime of t cross r double prime of t. Take the magnitude divided by the magnitude of r prime of t cubed. So this does not look simpler, but trust me, in practice, it almost always is easier to calculate. Unless you're dealing basically with helices. That's about it. I'm not going to derive this. You can look in the book if you want to see a derivation, but this is going to be this one formula, you'll be able to calculate curvature for anything relatively simply. Yeah, we got time. Let's do an example really quickly. So suppose our curve is given by t squared, t cubed. I invite you to try to use the previous formula for this one. You're not going to have a fun time. We'll say that much. Okay. So let's calculate the curvature function. Right, the curvature is going to depend on the point. It's going to depend on what value of t you plug in. So we're going to get some function. Let's calculate the curvature function. So to do this, we're going to need r prime, r double prime, the cross product. And then we're going to need magnitude r prime t. So let's find those. So r prime t is going to be, so we take the derivative component by component. So 1, 2t, 3t squared. R double prime t, take the derivative again, component by component. We get 0 to 6t. Magnitude r prime t is going to be square root of the sum of the component squares of r prime t. So 1 squared plus 2t quantity squared, so plus 4t squared, plus 3t squared squared, so plus 9t to the 4. Square root of all that. And then r prime t cross r double prime t. So we get 1, 2t, 3t squared, cross 0 to 6t. And really quickly, when we do that, we get 12t squared minus 6t squared, so 6t squared. 0 minus 6t, so negative 6t, and then 2. So the learned curvature is going to be the magnitude of that guy. (6t squared negative 6t2) divided by magnitude r prime t cubed. And so we're going to get not the prettiest thing in the world, but we get, so 4 plus 36t squared plus 36t to the 4 divided by, so r prime t is square root 1 plus 4t squared plus 9t to the 4. So that cubed is just all of that. We'll set to the 3 halves. And that's our curvature formula. So in particular, at time t equals 0, so in other words, at the point 0, 0, 0, the curvature is just going to be, well, you plug in t equals 0 into your curvature formula, and you get square root of 4 over 1 to the 3 halves. So you just get 2. But once again, this is really just a matter of memorizing this formula. It's magnitude r prime t cross r double prime t divided by magnitude r prime t cubed. How'd I get to that step? Well, from this formula, we just need the cross product, r prime and r double prime, and then the magnitude of r prime. And so this is the magnitude, lovely, magnitude of the cross product on top. Yeah. Okay, so everything I said about curvature boils down to, remember that formula, essentially. Okay, so let's look at a couple other geometrically important vectors. So let's look at the unit normal vector. So we have the unit tangent vector. Another important vector in relation to a curve is going to be the unit normal vector. So the unit normal vector is just going to be, you take the unit tangent vector, take the derivative, and then you turn it into a unit vector by dividing by the magnitude. Okay, so from this formula, it's not immediately obvious what the relationship between the unit normal and unit tangent vector are geometrically. But note the following. So if we look at the unit tangent vector and we dot it with itself, so if we take a vector and we dot it with itself, what do we get? What does that represent in terms of the vector? So it's related to the magnitude, right? This is something you should remember. It's the magnitude squared, right? So t dot t is the magnitude of the unit tangent vector squared. But what's the magnitude of the unit tangent vector? It's 1 for all values of t, right? That's by design because we turn it into a unit vector. So if I take the derivative of the magnitude of the unit tangent vector squared, well, that's a constant 1. The derivative of any constant is going to be 0. And then if we use our derivative rules for the dot product, right, our product rule here, this is just derivative of the first dot the second plus the first dot the derivative of the second. So this is t prime t dot t of t plus the first t of t dot the derivative of the second. Let me make that more obvious. So that's derivative, that's derivative. But the order, so these both involve t and t prime. And the order you take the dot product doesn't matter, remember? U dot v is the same as v dot u, right? So these are both the same as t prime of t dot t. So this is just 2 times t prime of t dot t of t. So when you dot the unit tangent vector with its derivative and multiply by 2, you get 0. So in other words, t prime of t is orthogonal to t of t because their dot product is 0, right? They're perpendicular. Well, t prime of t is orthogonal, so is t prime of t divided by magnitude of t prime of t. All you're doing is you're taking that vector and you're scaling the magnitude, but it's not changing the direction. It's still going to be orthogonal. So the unit normal vector is going to be orthogonal to your unit tangent vector. So here's what this looks like. The unit normal. So it's at every point orthogonal to the unit tangent. And the unit normal is going, so the unit tangent points in the direction of travel. And the unit normal is going to point towards, let me see, what is the best way to put this? So the book says inside of the curve. I would say it's going to point towards the direction you're changing. Right, so if you're turning, it's going to point in the, let me say, towards the direction of turn. It's going to point in the direction you're turning. So this is our curve. Let me do it this way. So if this is our curve, and suppose we're traveling in this direction along our curve. So right here, it's not very tangent. That would be our unit tangent vector. That's the direction we're going. And the unit normal would be orthogonal to that and would point in the direction we're turning, which would be that way. Whereas right here, that's our unit tangent vector. Now our unit normal is going to be pointing the opposite direction because now we're turning that way. But in all instances, it's going to be orthogonal to our curve. And so that's geometrically what's going on with the unit normal vector. It's orthogonal to the unit tangent, and it's going to point in the direction you're turning. So because it's convenient, it has some other geometric uses that are a little less straightforward to explain, but I won't bother. We have a third vector, if we're in R3, called a binormal vector. So we use a capital B for that. And that's just going to be the unit tangent cross the unit normal. So this is going to be a vector which is orthogonal, obviously, because it's the cross product of the two. To the unit tangent and the unit normal. And we like unit vectors in this case. So you might be wondering why we're not dividing by the magnitude in this case. And that's because you can check this is automatically a unit vector. You don't need to divide by the magnitude. Automatically unit vector. And you can look in the book to see why. It's pretty quick, but I don't want to spend too much time on it. And that's all I'm going to say about the binormal vector. Just remember it's t cross n. So the unit normal vector, t prime divided by magnitude t prime, unit tangent, r prime divided by magnitude r prime, and the binormal is the cross product of the two. So just unit tangent is r prime divided by magnitude r prime. Unit normal is t prime divided by magnitude t prime. And the binormal is t cross n. And just so we can remember, the curvature function is going to be magnitude r prime cross r double prime divided by magnitude r prime cubed. So these are the three things, the four formulas you need to remember from today. Okay, so very extremely quickly. If you need to go, that's fine. I'm going to do a really quick example, finding the unit tangent, unit normal, and binormal vectors for a helix. So r of t is going to be 2 cos t, 2 sine t, t. It's going to be a helix. So let's find the unit tangent, unit normal, and binormal vectors. So we're going to need to do these step by step. So first, you need to find the unit tangent. So for the unit tangent, you need r prime. So r prime t is going to be negative 2 sine t, 2 cos t, and 1, taking the derivative component by component. And what's the magnitude r prime t going to be? What do we get? Square root 5, correct. So unit tangent is r prime t divided by magnitude r prime t. So it's 1 over root 5, which is the magnitude. You know what? Let's just bring that 1 over root 5 inside. So we get negative 2 sine t divided by root 5. So negative 2 over root 5 sine t, 2 over root 5 cos t, and then 1 over root 5. So then we do the same thing. So for the unit normal, we need the derivative of t. So t prime t is going to be, take the derivative component by component, negative 2 over root 5 cos t, negative 2 over root 5 sine t, and then 0. So when we take the magnitude of that, we get 2 over root 5, which you can check really quickly. So when you divide t prime of t divided by magnitude, or by the magnitude, so t prime t divided by magnitude t prime t, which is the unit normal, we just get rid of the 2 over root 5s inside. So we get negative cos t, negative sine t 0. So we found t and n. Now we need to find b, which is going to be their cross product. So we get the cross product of, so we get negative 2 over root 5 sine t, 2 over root 5 cos t, and then 1 over root 5. And then n was negative cos t, negative sine t, 0. And when we take that cross product, we get 1 over root 5 sine t, so negative 1 over root 5 cos t, and then 2 over root 5 sine squared plus 2 over root 5 cos squared, which is just 2 over root, stop calling me, I don't care. So that is 2 over root 5. And that is our binormal vector.
Can you go back to the previous slide just really quick?
Sure.
Thank you.
Yeah, I flew through this, so my apologies. But really, this is all very, very simple. It's just a matter of remembering those formulas on the previous page. Okay, so that's it for today. Tomorrow we're going to talk about motion in space, which really is not that much new. We've kind of already talked about all of that stuff. And that will be the last of the stuff on the exam. So I'm going to go over to the Zoom meeting for office hours. If you have any questions, I'll see you there. If not, I will see y'all tomorrow. Have a great day. And yeah, see you tomorrow.
Thank you.